All right, thank you for joining me on this Monday morning. Let's talk about bases. So do you guys have any questions about acids before we move into bases? So remember, what you need to know about acids is not necessarily the pKa's, although they will be very, very helpful, but instead the general rankings of those things. I think that probably memorizing the pKa's would be really helpful, but if you don't and you know those rankings down, you will be able to make it through. Also, thankfully, if you remember 35 or memorize 35 and you accidentally do 36 or 32 or something like that, the rankings are still going to be the same. So you don't have to know the exact numbers. In fact, I've given you pretty oversimplified numbers, and I've tried not to make them all ranges, but just to kind of have whole numbers. So they're all pretty well spaced out. So hopefully that is helpful. The most important thing about today is that if you know your rankings of your acids, you will know the basicity of their conjugate bases. So that table that we did on Friday, where we just had those acids all ranked kind of from strongest to weakest, that doesn't tell us how basic those molecules are. It tells us how basic their conjugate bases are. So we want to always think about those things as reactions. In fact, let's skip over really quick to what we did on Friday. So on Friday, what we did, and this should all just be written out, you shouldn't have to write all of this down again, is we looked at those acids and we ranked them. At the very top was like sulfuric acid. And then we had a bunch of other things in between, like there was H3O plus, and then we went down, there was H2O, et cetera, and there was like, at the very bottom, we had an sp3CH. Right? Okay, and we had our pKa's here. And so the pKa of sulfuric acid is about -9, and for hydronium, it's about -2, and for water, kind of depending on who you believe, it's 14 or 15.5 or whatever, but let's just say 16. And then at an alkane, it would be about 50. So those are the pKa's of those. So if you have all of that down pat, that doesn't tell you about the basicity of these molecules, but it does tell you about their conjugate base. So I beat this into the ground, I think, on Friday, that we want to consider not just the acid, but what it becomes after it acts like an acid. So it'll always turn into the conjugate base. So an acid always loses a hydrogen. This one would become HSO4 minus. H3O plus, if it lost a hydrogen, would become what? H2O, right? And H2O, if it lost a hydrogen, would become what? OH minus. And then if a CH lost a hydrogen, it would become a C minus, which is incredibly unstable. So when we have the pKa of this acid, we know the pKb, or can calculate the pKb of its conjugate base. So you do not have to memorize any pKb values. Even if you choose to memorize the pKa values, just know that solving for the pKb of the conjugate base is just doing 14 minus that thing. So what is 14 minus -9? Because that'll give us the pKb of this molecule here. All right, we're gonna do some math here. It's not gonna be hard math. 14 minus -9 is 14 plus 9. 14 plus 9 is 23. Okay. All right, the pKa of H3O plus is -2. So the pKb of water would be 14 minus -2. So 14 plus 2, which is, you guys can do this. Correct, Caleb, +1. All right, Olivia, are you ready? What's 14 minus 16? Great. All right, Savannah, what's 14 minus 50? Yes, correct, -36. All right, so if we know the pKa of these molecules, it's pretty easy not to find their pKb, but the pKb of their conjugate base. And so it's always about the relationship between an acid and its conjugate base. It's not about using water to figure out its pKa and its pKb. It's about using the pKa of water to find the pKb of the hydroxide, using the pKa of hydronium to figure out the pKb of water. So we are always using these guys as conjugate pairs, that is to say one with a hydrogen and one without, to figure out the acid, the pKa of the acid, and the pKb of its conjugate base. Does that make sense? So just overall looking at these things here that we have drawn, we knew already that sulfuric acid was a really strong acid. So what that tells us is that it really wants to react and give away its hydrogen. It's very reactive. Everybody good with it? All right, so that would mean that what it becomes after it gives away a hydrogen is really stable. And so HSO4 minus is really stable and does not want to go backwards. So if we're thinking about the equilibria here, this guy goes basically 100% towards HSO4 minus, which would mean that HSO4 minus does not want to go back. All right, H3O plus has a pKa of -2, which means it is very acidic. It's a strong acid. So it is also going to go pretty much 100% towards product. And really, water does not really want to go back. Let's say that for this one, we might have a little tiny arrow going back, but so minuscule that you can't really make it out. All right, when we get to water, does water want to react as an acid? Does it want to give away a hydrogen? No, this number is very positive. So no, it doesn't. So it's not a very strong acid. Therefore, its conjugate base would be pretty strong. And hydroxide, we do know that hydroxide is a pretty strong base. It does like to react. So this reaction would like to go backwards. How we doing? All right, going down to this CH. This was the worst of our possible acids. So does it want to react? Absolutely not at all. No, never. Does not want to, will not, hates it. Okay? So what would that mean about its conjugate base?
It would really want to react.
Exactly. It really, 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 really wants to go this way. So these are all about equilibria. And if you want to go one way, you don't want to go the other way. And if you don't want to go forward, you would want to go backwards. So that's what equilibria is all about. And acid base is all really just equilibria. That's why we use those big Ks. All right. So looking at these values, here's what acids and bases have in common. A negative value means they really want to react. So sulfuric acid has a very negative pKa, which means it very much wants to go away from itself. Because strong means reactive. A strong acid is a reactive acid and would have a low or negative pKa. On the flip side, a strong base is very reactive and would have a low or negative pKb. So a K is still telling us equilibrium constant. So whether we're looking at pKa or pKb, a very negative value means it is very reactive. So a very negative pKa is a very reactive acid, strong acid. A very negative pKb is a reactive base or a strong base. So there are a lot of things in here that seem like they're inverted or inversely proportional, and that is true. But these pKs and what they mean, those are not. A negative value is very reactive. A very positive, large positive value is not very reactive. So just kind of looking at these things, we can see that hydroxide is a strong base, really wants to react. It has a negative pKb in the same way that H3O plus is a really strong acid. It has a negative pKa. Sulfuric acid is a strong acid. It has a very negative pKa. This thing right here, the C minus, is ridiculously basic. It has an incredibly negative pKb. So this is so basic, it doesn't even exist. It's so reactive that we can't have it in any, you can't make it. So you might say, well, that's the strongest base. Why don't we use that all the time? Well, it's so strong that we just can't even make it. So it's kind of ridiculous. Hydroxide right here, hydroxide is kind of what we learned from Gen Chem, is the classic strong base. And it's what we use in lab very often as a classic strong base. But there are much stronger bases because there are values much lower than -2. And that's what we'll kind of look at today. All right, so how are you feeling? So the bridge assignment went, I'm going to stop there without an adjective or adverb. It went, but we're going to walk through this, but this is the stuff that we need to keep in mind. We're looking at the relationship between a pKa of an acid and the pKb of not that molecule, but its conjugate base. All right, so let's go back to the bridge assignment. All right, so I just started straight off with the fact that we've got water here, which can act like a base. And if it acts like a base, all bases share electrons with an H+. They become protonated, and it would become H3O+, which is the conjugate acid. So once again, this is an acid-base pair. We're looking at it here from the base perspective, but we could easily look at it from the acid perspective as well. The point is, it's just going back and forth. So the pKa of H3O+ helps us to figure out the pKb of water because they are an acid-base pair. So the pKa of H3O+, and we just did this one a second ago. What's the pKa of that one? -2. And so therefore, if that thing's -2, 14 minus -2, it's 14 plus 2. So the pKb of H2O is 16. That's it. So you got your pKa's of your conjugate bases, or sorry, the pKa's of your conjugate acids, you can figure out the pKb of your original base. So let's do that for all of these molecules. So these are 5 bases, and what we want to do is think about them turning into their conjugate acids. So we'll add an H+ to all of them and look at what they become. So once again, all of these are your bases. All right, if you start off with hydroxide and add an H+, what do you get? H2O, lovely. And what is the pKa of H2O? Great. All right, if we start off with that carboxylate and we add a hydrogen, we would get CO2H, or carboxylic acid. What is the pKa of a carboxylic acid? 5-ish, right. All right, if we start off with this C- at the end of a triple bond and add a hydrogen, we would just get a C triple bond CH. So that's an alkyne. The pKa of an SPCH is 25, lovely. So you can do this correctly. You can get these ranks if you don't know your pKa's. But I think that knowing the pKa's makes it easier. All right, here is, if there's one place where you guys are gonna trip up, it's right here. And that's because these are really tricky. We have neutral nitrogens, negative nitrogens, and positive nitrogens. And they exist in 2 separate equilibria reactions. We could have the neutral becoming positive, which is what we would have here. And we could have the negative becoming neutral. And those are 2 completely independent reactions. So what we will need to do here is know the pKa of a positively charged nitrogen and the pKa of a neutral nitrogen. And we can use them to figure out the pKb of a neutral or a negative. All right, and it doesn't matter how many hydrogens are attached. So an NH4+ is going to have about the same pKa as an N+ with 3 hydrogens and 1 carbon. It doesn't really matter. It's all about the fact that it's an N+. So what's the pKa of an N+? Yes, it's approximately 10. And with more or less carbons attached, it's more closer to 9 or closer to 11, but they're all around 10. All right, what about a neutral nitrogen? 35, great. All right, so once again, these are the pKa's of our acids. And we use these to get the pKb's, not of those acids, but of their conjugate bases. So we used OH-. We said if we add a hydrogen, it becomes water. Well, if we know the pKa of water, we can figure out the pKb of hydroxide. So the pKb is how you do it. 14 minus your pKa of your conjugate acid. So the pKb of water, or sorry, of hydroxide, and this is of the original base, so of hydroxide. pKb is what? What's that? It's 14 minus 16. It's okay. Yes, that's correct. Hold on to that a second. So for a carboxylate, which is the base, we drew out the acid and said the pKa of the acid was 5. So the pKb of the base is 14 minus 5, which is, yes, exactly. Perfect. So it's all about this relationship here, the pKa of an acid and the pKb of its conjugate base. So if you look at it starting here, this is exactly what we did on Friday. On Friday, we basically started here and we turned it into a base, but we just looked at the pKa's. Today, we're kind of looking at the base and thinking of it turning into its acid. It's the same pair whether you go forward or backwards. All right, so we know that for an alkyne, the pKa is 25. So for a C minus at the end of a triple bond, an SpC minus, the pKb would be 14 minus 25. Negative 11. All right. So this is the tricky ones, I think. But here we are looking at the pKa of a positively charged nitrogen, which we can use to figure out the pKb of a neutral nitrogen. So if the pKa of a positively charged nitrogen is 14, then the pKb of a neutral nitrogen would be what? 14 minus 10. 4. You gotta say it real loud. Oh, I'm not trying to. What's the worst thing that could happen if you're wrong? Yeah. But I would say with a smile on. 4 is correct. That's amazing. Look, the benefits of being right are so much better than the drawbacks of being wrong. Thank you. Sorry, I just couldn't hear you. That was all. All right. So yeah, it's just 4. So notice that all of these values that are kind of between 0 and 4, they all add up together. It's only when you get one of them negative that the other value strays above 14. All right. So this one's crazy. So if the pKa of a neutral amine is 35, then the pKb of a negatively charged amine is 14 minus 35. Negative 21 is correct. That's very negative.
That's weird how the NH3, the pKb and the pKa aren't the same.
Yes, so both of these are pretty reasonable in terms of the fact that they're all kind of around 7-ish, but this thing is ridiculously weakly acidic, so therefore this N minus is ridiculously strongly basic. In fact, when we look at these values, once again, the more negative, the stronger you are of whatever. So a really negative pKa, which I didn't give you any that had a negative pKa, but this carboxylic acid at a 5, this would be the strongest acid on this list. Therefore, its conjugate would be the weakest base on the list. So the ranking of the conjugate acids and the ranking of their conjugate bases would be inversely proportional. All right, so looking at these numbers though, straight up, the relative basicity, so the most strongly basic of all of these is what? We're going red, we're committing to this. What number is most negative? Yes, so this is by a huge margin, your number one strongest base of this list. All right, and then you just go in order. Next would be number 2 is your negative 11 here. That is that C triple bond C minus. And then your negative 2 of hydroxide would be your 3rd on this list. And then after that, you would have your neutral nitrogen. And then your negatively charged oxygen. Oops, I put a wrong number, that would be 4. And so all of these numbers are exactly inversely proportional to our acidity rankings. So I didn't ask you to do this, but if you rank these acidity, the number 5 is your strongest, and then 10 would be 2nd, and then 16 would be 3rd, and 25 would be 4th, and then 35 would be fifth. And so notice that these lists are exactly inversely proportional. All right, I need to pause for a second because my PC is running out of juice. I need to go grab that. All right, so there should be a couple of weird things about this list. I picked these molecules on purpose because I want you to kind of think about the fact that in Gen Chem you talk about one strong base, and we think about one strong base, which is sodium hydroxide. Is that a strong base? Yes, that is still true. That's this thing right here, hydroxide. Its pKb is -2, which is strong. But compared to that, a C- is way stronger. This is 1 billion times stronger of a base. And compared to that, an N- is another 10 billion times stronger. So an N- is ridiculously strong. We will use N-. In fact, we have used N- a lot. I'll show you where in a second. LDA is an N-. It's a ridiculously strong base. It's way stronger than sodium hydroxide. So the cap on these things is not 0 to 14. It goes really far in any direction. It's also worth noting that our strongest acid has a pKa of -9. Our strongest bases have pKbs way lower than that. So this thing is super strong of a base. All right, in last semester, we didn't get into great depth about acid-base, even though it seemed like we did at the time. But we compared things strictly by structures, really just kind of comparing apples to apples. So comparing an O- versus an N- versus a C-. Well, what we've added now is we've added that there's multiple different environments of C- where they can get more or less acidic, more or less basic. The same thing is true of oxygens and nitrogens. And sometimes they show up in weird places in lists. In general, last semester, we considered that an O- would be more reactive than any neutral species. But look at our list here. It should be no surprise that N- is the most unstable. That should track from last semester. O- is less stable, is really, really unstable. But notice here that this C- in this situation is actually more stable than a regular N-, which kind of bucks our trends a little bit. But the complicating factor here is the hybridization. So there's multiple competing trends, and you just need to know these orders to be able to get these right. Hopefully it makes sense that an O- with resonance would be more stable, so less reactive than an O- without resonance. But one thing also that's really weird is that an O- with resonance is more stable than a neutral nitrogen. You see that? Our neutral nitrogen was only our fourth weakest, I guess fourth strongest, so second weakest base, but a carboxylate is even weaker. So this O- with resonance is actually more stable and less reactive than a neutral nitrogen, which is weird. So a lot of these don't exactly follow the trends that we're used to because there are complicating factors to this. And this is why we have to just kind of learn those pKa's and learn those rankings because those were determined experimentally. So there are rationales that we have come up with for a lot of these, but for some things, you're really just comparing apples to oranges and you just need to know some numbers because the only way to figure it out is to have someone go in the lab and figure out these numbers for us. All right, questions on any of that? So acid-base pair, it's something we're gonna do a lot today. So my goal for the rest of today is just to practice. I don't have anything else to tell you about this. There wasn't really a video to make. Basically, it's just the pKb of a base is 14 minus the pKa of its conjugate. But it's not, it is that simple, but it takes a whole lot of steps for you to get there. There's a lot of little things you need to be able to do and do them correctly. So I think the best way to do this is to practice. So let's go into I was telling everyone before class, but I'll tell you, those of you in Zoom and still here, acid base is complicated. And there's a lot of little steps. And each of those little steps is not altogether too challenging if you know exactly what you're doing. But for the most part, you're putting together so many of them that it's easy to have things get overwhelming. And I'm sorry about that. Acid base is absolutely worth practicing. You know most of the background information, but it's a whole lot of little steps and you have to do them all right. So don't feel bad if this gets really overwhelming. But just take steps back. I find myself still asking those basic questions of what's more basic, an OH minus or an OR minus? Well, Josh, what's the fundamental problem with a negative charge? It's got too many electrons. All right, what do carbon neighbors do? They share electrons. But if you got too many electrons, you have a neighbor donating, does that make it worse or better? It makes it worse. It makes it more unstable. Okay, so does that make it more reactive or less reactive? If you're more unstable, you'd be more reactive. All right, so an O minus next to carbons would be more reactive than an O minus without. And so an O minus would be a stronger base than an OH minus. And that's a lot of little steps. I still walk through those steps. So it's okay, but take the time to walk through them. It is a lot of little steps. You can do it. If you memorize all your pKa's, it might mean that you don't have to take as many of those steps, but at least gives you a framework to work from. All right, so let's consider our 4 bases that we'll see the most often. Sodium hydroxide, LDA, which is this guy, Li plus, and an N minus with 2 isopropyl groups. Move me out of the way here. All right, and then potassium terbutoxide, TBUOK. That is a K plus and terbutoxide. Then TEA. So these were kind of these bottom 3 are our classical bases that we use for elimination because they're bulky and non-nucleophilic. And then sodium hydroxide is, of course, just OH minus. All right, let's rank these in terms of basicity. So how would we do this? Okay, we can find their pKb's, absolutely, yes. So to find their pKb's, we need to draw their conjugate acids and find their pKa's. If you can rank their pKa's, then you can either find their pKb's and rank them, or if you just rank the acids, you just flip the numbers for the bases. Either way is fine. But let's go through and do all of that. You might also, for a lot of these, just be able to look at them and figure out based on what's more stable or less stable, what's more reactive or less reactive. Sometimes that works when you're comparing apples to apples. And in this case, we actually are, so we could do that. But it's worth walking through the process. So if these are bases, bases always gain an H plus. Then we will draw their conjugate acids. So OH minus and an H plus would become water. That N minus, when it gains an H, it's just going to become a neutral NH, so I'm not even going to draw its other stuff. Get used to just considering neutral nitrogen, negative nitrogen, and positive nitrogen. Don't really worry about the number of hydrogens around it. All right, an O minus, when it gains a hydrogen, would just become an alcohol. And then a neutral nitrogen, when it gains a hydrogen, will become what? N plus, great. And yes, those are all ethyl groups there. And yes, those are both isopropyl groups there, but we're just focusing on the N plus versus the N neutral. All right, so do we know our pKa's? The pKa of water is what? 14, 16, sure. What do you want to go with? You're on team 14. That's fine with me. All right. The good thing is if you use 14 or 15.5 or 16, you'll get the same ranking, so it doesn't really matter. For an NH, what is the pKa of a neutral nitrogen? 35. Perfect. Good job. All right. What about for an alcohol? 16 to 19. You want to pick a number? Okay. That's fine. Guess what? This one's closer to 19. Guess what? It doesn't matter. You'll still get the answer correct as long as you're in the range there. All right. The last one here is an NH. This is an N plus with an H. So the H doesn't really matter. It's all about that plus charge. So what is the pKa of an N plus? 10. Great. If you can remember these two, neutral nitrogen has a pKa of 35 and positive nitrogen has a pKa of 10. It's going to help because that's just, it's not the only mistake that people make, but it's a really, really, really common one is to mix those up. All right. So here's what we could do. We could rank these. The strongest acid of these four would be which one? Yeah. And hopefully that should make logical sense that an N with a plus charge would rather become neutral than any of these becoming negative. And that's true. All right. That's also shown with their values. So this one is 10. And then this one would, the 14 would be 2. The 16 would be 3. The 35 would be 4. And so we could use that information and we would just flip all of these numbers for their conjugate bases. Right? Or we could go through and figure out their pKb's. Whichever way you approach, you'll get the same answer. So let's do this here. The pKb, just for the sake of completeness, 10 minus 14, this would be 4. pKb here, 10 minus 16 is about -2. For an N minus, we did this one a second ago, it's 14 minus 35, which is -21. And for hydroxide, we went with 14, which is fine. 14 minus 14 is 0. So there's all of our numbers. And notice that these are going to go in the proper order. Your -21 would be your strongest base. So this would be our number 1. Our -2 would be our second strongest base. Our 0 would be our third strongest base, and our 4 would be our fourth strongest base. All right, looking at these values, it probably seems like all of the negative charges should be super strong, and then neutral would be kind of weak. And in general, that's true, but notice that the N minus is way, way, way stronger than any of the rest. And the difference between 4 and 0 and -2 is actually not that huge. A neutral nitrogen is less basic than an O minus, but not by that much. But that's the rankings that we get. So doing these pKb's was actually unnecessary for figuring out our rankings, but it does give us some information kind of about how close they are to each other. Does that process make sense? If you know your pKa's, you can do this. If you knew these rankings without knowing the pKa's, you could still do this. But I, again, highly recommend you learn those pKa's. All right, let's do some more examples. All right, so let's do some that might not be quite as readily, I don't want to say obvious, but we'll do some definitely comparing apples to oranges here. I will splash in. Maybe that's good. Do a long owners. All right, so once again, let's compare these things in terms of their basicity. So we are absolutely not comparing things straight up here. We've got an N minus with no carbon neighbors, an O minus with carbon neighbors, a C minus with resonance, and a C minus that's SP. So in this case, the only real way to do this, you're not going to really have a lot of chance by just looking at these and saying, well, O minus is more stable than N minus is more stable than C minus. That doesn't quite work. We need to get a little bit more nuanced in this case. So we do need to know what those conjugate acids are and what their pKa's are. So once again, let's add in some H pluses. And draw out what they would become when they are bases. Boop, 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 do. That's our hydrogen we're talking about. Here we would have an NH3. And that's the hydrogen we're talking about. This one is a little bit different. That's the hydrogen we're talking about. And here, this would be an OH. And that's the hydrogen we're talking about. Okay. So we know the pKa of this one, hopefully. We mentioned it already. It's the pKa of an H at the end of a triple bond. 25. My hope is through some repetition today, we'll be in good shape. What is the pKa of a neutral nitrogen? 35. Lovely. All right. What about this? What's this thing's situation here? The CH next to a ketone. Yeah, it's 20. So the key here is that it's that one spot over from a carbonyl. And then when it is a C minus right next to a carbonyl, it has resonance with the oxygen, which makes it the most stable of all of our C minuses, which is actually going to make it the weakest base of all of our C minuses. It is therefore the most acidic of all of our CHs. The pKa here is about 20. All right, and then lastly, we've got an alcohol there. What's the pKa of an alcohol? 16, 18, something like that. Okay, we'll just call it 16. All right, so looking at these, which one, so I'm not going to rank these for you. Which of these four molecules is the most basic? Sydney, what do you think?
I'm gonna go with NH3.
We're looking at the basicity of the minus charges that you started with.
Oh, NH3.
Yes. So if given our acids, the conjugate acid that is least acidic is NH3, then the compound that would be most basic and least acidic go together in pairs. So yes, this would be your number one. The pKb would be negative 21. All right, Caleb, what's next? C triple bond C minus, right? That's what you meant? That is the 2, correct. All right, Olivia, what's next? Yes. All right. I'm not going to call on anybody for this one. I'm going to say this is number 4. Sorry. All right. So notice that in this case, your O minus is the most stable. But as we look at the trends in the periodic table, O minus is more stable than N minus. N minus is more stable than C minus. And in general, that is true when all other things are the same. So if they were all sp3 with no resonance, that would be true. But notice that because this one is sp, this C minus is actually more stable than an N minus, so less reactive. This C minus is also more stable than an N minus, and therefore less reactive. So it's not quite as simple as N minus versus C minus versus O minus. There are mitigating factors depending on resonance, depending on hybridization. But if you didn't try to do it just by mentally figuring it out and instead drew out the acids, knew their pKa's, filled it in, flipped them, you got the right answer without having to commit too much to trying to sort through all of these competing trends. Questions on that? How we doing? All right, let's move on a little bit to equilibria. So an equilibria reaction involves an acid and a base getting together to make a different acid and a different base. And this is something that we looked at last semester. It's still true, but now we just have more pKa's. We have more ways to evaluate this, or more data to use to evaluate. All right, so if I add sodium hydroxide to, let's say, I'm going to use this thing right here to an alkene. And I want to try to pull a hydrogen off to give me water plus a C minus at the end of an alkene. There would be a backwards reaction in which this grabs a hydrogen off of water and would just go backwards again. So all acid-base reactions are theoretically reversible. So the question would be, does this tend to go forward or backwards? So which side would the equilibria lie on? The way we did this last semester, I'll wait until you write it down. We'll go from there. So last semester when we did this, we just looked for the more stable ion. And that is still true. Equilibria will go towards the weaker, less reactive, more stable things in general. But we've got more nuance this semester, so we need to really look at comparing bases versus bases or acids versus acids. The good news is that whichever side has the weaker acid will also be the side that has the weaker base. Whichever side has the stronger acid will also be the side that has the stronger base. So you can look for the side with the stronger versus the weaker base, or the side with the stronger versus the weaker acid. And since we've kind of geared everything around acids anyway, that's what I would recommend you do, is look for the acids. So what's the acid on this side? Who's losing a hydrogen? All right, sodium hydroxide, is that an acid or a base? It's a base because it's gaining a hydrogen, right? So who's the acid? The other thing, yeah, the alkene. So acids lose hydrogens, bases gain hydrogens. So this is going to be our acid on this side. All right, who's losing a hydrogen on the other side? The water. So the water is the acid over here. All right, so what is the pKa of an alkene, or an sp2CH, versus the pKa of water? Again, if you know the rankings, it suffices, but let's see if we can know the numbers. The alkene's atrocious. It should be near the bottom of your list. Yeah, 44. That is not very acidic at all. What about for water? 16. All right. So let's use that because we still haven't quite answered the question yet. We're getting there. What does a pKa of 16 versus 44 tell us? One of them is way more acidic. Which one's way more acidic? Yes. So by a strong amount, this is a stronger acid. And therefore, your alkene would be a weaker acid. So stronger means what? More reactive or less reactive? More, right? Would you rather spill a strong acid on yourself or a weak acid? A weak acid, because it wouldn't try to react with you relatively. A strong acid would. It's very reactive. So a stronger acid is more likely to react. So a stronger acid would push the equilibria away from itself because it wants to react. A weak acid is more fine where it is. So which way would this equilibria tend to go? Towards reactants or towards products? Exactly, towards reactants. And in this case, those numbers are hugely different. So this reaction is going to go 100% to the left. Don't think of it as really going backwards. Think of it as either going to the right or to the left. So if you were to combine, does that make sense? You go away from the strong acid towards the weak or less reactive side. And if we wanted to, we could figure out the pKb's for these. The same trend would be true. All right, let's think about this logically. What's more stable, an O minus or a C minus? O minus. And note that no matter what we do, if you look at all of those values on our charts, all of your OHs are more acidic than your CHs, meaning that all of your O minuses on there are more stable than your C minuses. We get into some weird territories between carbons and nitrogens, but all of your OHs are going to be near the top compared to your CHs. So that's still true. It goes towards the O minus because O minus is more stable than C minus. So all of those different trends are correct. What that would mean is if you took an alkene and you added hydrogen peroxide or sodium hydroxide, would anything happen? Would you go towards product? No, you wouldn't. So nothing would happen. So they would just stay where they are. You would put these two things in a vial together and they would just sit there. Questions on that?
So if you gave us this, but you only gave us the reactants, we would put no reaction? Or do you want us to put things like to draw it out?
Yeah, if I was asking you acid base, and this is, look, it's in the homework as well, like to draw the products of these acid base reactions and then just ask what would happen. Where would the equilibria lie? Not quantitatively, these are starkly different numbers. So you would get 0% forward, but regardless, those are values. And whether or not you know the values, this one is definitely weaker. This one is definitely stronger. So it would push away from the stronger towards the weaker. All right, let's do another one. What if we were to combine LDA plus acetone? And I can draw these for you if you want. Okay, so acetone is a ketone. It looks like this. And LDA is an N minus with lithium. All right, so what are the products and where would the equilibria lie? So Savannah, acetone, not super reactive. LDA is an N minus, which is very reactive. Is it very reactive as a base or very reactive as an acid? What do acids do? It's all right, so we can't remember. Here's what I always go back to, and I do this as well. Tell me one acid, go. Something that ends with the word acid. Something acid. Great. Will you remember that one? I remember that one. HCl, hydrochloric acid. Is that going to gain a hydrogen or does it lose a hydrogen? Yeah. So go back to that. If you get stuck, go back to something you know. Right? Hydrochloric acid is usually the first acid that pops into people's minds. And we pretty much remember this correctly, that it splits into H plus and Cl minus because acids lose hydrogens. Bases, on the other hand, gain hydrogens. So one thing we talked about a lot last semester and a little this semester is that negative charges are nucleophiles and bases, right? Because they have too many electrons, they want to share them. All right, so we're gonna go back and try this again. You ready? N minus is a strong what, acid or base? It doesn't even have any hydrogens to lose. Yes, negative charges are strong bases. That's still true here. So that is going to be your base for sure. So by process of elimination, acetone has to be your acid. So Kylie, where can we pull a hydrogen off of this acid? Sure. Yeah, you can't do anything wrong here when you treat this as an acid because the acidic spot, the most acidic CH, we don't have any OHs. All of the hydrogens here are either right there or right there, and they're all symmetrical, so it wouldn't matter. But we're pulling a hydrogen off of an alpha carbon, and that should hopefully jog your memory a little bit. So when we do that, your LDA would become neutral, and your acetone would become a C minus at an alpha position. Everybody following? All right, so the acetone is the acid on the reactant side. Which of these over here would be the acid? Yeah, the thing that LDA became. A base always becomes an acid, so the acid would become the base. Furthermore, there's our negative charge. And the negative charge is going to be your base once again. So base. So what we want to do is rank the pKa's of our two acids. So the pKa of an alpha carbon, alpha to a carbonyl, is what? Sydney, go. Take a guess.
5.
How about 20?
Okay.
So that carbon with the alpha carbon right next to the C double bond O, that is your most acidic. It's the highest one on the list for carbons. It's 20. So it goes, the alpha carbon is 20, and then the triple bond is 25, double bond is 45, single bond is 50. Those are your 4 carbons. All right, what about a neutral nitrogen? 35, great. We were learning that one really well. Okay, so we got a 20 and we got a 35. Those are really different numbers. Which one is a stronger acid? The 20. Neither one of those is a strong acid, but 20 is a lot lower than 35. So this is your stronger acid. Does equilibria go toward a strong reactive acid or away from a strong reactive acid? Away. So equilibria in this case would push very strongly towards product. This is an important sneak preview reaction. I mean, this is just acid base. This is kind of the reason we're doing this acid base right now in the middle of all these carbonyl reactions, is because we can pull a hydrogen off of an alpha carbon, but only if we add a strong enough base to do so. And that would mean it would need to be a base that's strong enough to give you a conjugate acid that's weaker than this, which is a whole lot of words. It takes a very, very, very strong base to pull that hydrogen off. So we have to use something like LDA. All right, questions on that one? So it's a lot of steps. You need to be able to know what an acid is, know what a base is, know what an acid does, know what a base does, where you're more likely to have an acid, what you'll get afterwards. Draw all those things out, identify the acids and the bases, put out your pKa's, point towards the weak one. All right, I got one more for you today. This is our last example. All right, so it's a carboxylic acid and an amine. Which one do you think is more acidic? I'm gonna say that backwards. Caleb, this is for you. You ready? You've got an amine and a carboxylic acid. Which one do you think is the acid? The amine or the carboxylic acid? Correct. All right, so the pKa of an amine is like 35 and the carboxylic acid is 5, so it's way more acidic. Carboxylic acids are quite acidic for our functional groups. So this is going to be your acid. It's going to tend to give a hydrogen away, which is what acids do. So in the product, we would end up with a carboxylate and an N+. All right. Quick glance, quick call. Olivia, what do you think is going to be preferred? The neutral side or the charged side? It makes sense, right? It completely makes sense. All right, here's what the numbers tell us. Here is your acid over here. Your acid on the right side would be the N+. The pKa of a carboxylic acid is approximately what? 5. What's the pKa of an N+? Yes. So which one is a stronger acid? Correct. So this is your stronger acid. So which way would equilibria go? Exactly, towards the products. So the equilibria prefers products by a factor of 10 to the 5th, which is about 100,000 to 1. So this should be weird to you. It turns out that a carboxylic acid and amine would rather be O- with resonance and an N+ than neutral. Yeah, if you make a little squinchy face because that seems weird, that is weird, but it is true. And so what we see in our bodies is that we have a whole lot of molecules called amino acids. And amino acids all look like this. If you draw them out with an amine and an acid, whatever their R group is, they all have amines and carboxylic acids. But if you put a carboxylic acid and an amine together, they don't like to stay that way. Instead, they prefer to, in solution, where they can react with each other, or with another amino acid, exist like this. And your equilibria prefers to be a carboxylate and an N+ at the same time, as opposed to a neutral species, which is what we would probably expect or want them to be. So this is one of the weirdest and most biologically relevant things that we've added this week, is that when it comes to acid-base, carboxylates in solution prefer to be O- with resonance, and nitrogens prefer to be N+. So your amino acids, which is these are hugely important molecules to our bodies. They prefer to be positive and negative at the same time instead of being neutral. And this is what we find. So if you look up in your biology textbooks or biochemistry textbooks, this is usually the way that you'll see amino acids drawn. And you might think, well, why didn't we just make them the carboxylic acid and the amine? That's neutral, and we can just do that. Well, it's because this is biologically and physiologically the way that we find it, because of their pKa's and because of what they prefer. All right, any questions? You've got 3 extra minutes today, so good luck. I will see you all in lab today or tomorrow, or in class next Monday, or in class on Friday, or something like that. Have a lovely day.